SAS Demonstration Statistical Tests Part 2. The data set that we are going to be using for this demonstration comes from research by Afifi and Azin in 1972. Data was collected for 113 patients at the Los Angeles County Hospital Shock Unit. For each patient, data was taken on admission and either shortly before death or before discharge. The patient's survival status was also noted. The raw data for this study are contained in the file afifi.dat, and there are 2 lines of data for each person in the study. So you see here in our input statement, we have a number 1 and a number 2 indicating that there are 2 lines of data for each observation that's read in. And we're reading in the ID number, the age of each patient, gender, their survival status, what type of shock they experienced, their systolic blood pressure at time 1, their mean arterial pressure at time 1, their heart rate at time 1, a cardiac index at time 1, their urinary output at time 1, and their hemoglobin at time 1. And from the second line per observation, we're reading in the time 2 measurements. And then in the data step, I'm creating a categorical variable for shock. So I'm saying that if shock type equals 2, and 2 represents no shock, then shock equals 1. And if shock type are any of these values 3 through 7, then shock equals 2. Just so you know what each level of shock represents, 2 stands for non-shock, 3 stands for hypovolemic shock, 4 stands for cardiogenic shock, 5 stands for bacterial shock, 6 stands for neurogenic shock, and 7 stands for some other kind of shock. So this is the format codes that we're going to be using with our data. So the first thing I'm going to do is just print out the first 10 cases and also look at descriptive statistics of the continuous variables. So here is the printout of the first 10 cases in our data set. And you see that we have attached formats, and notice I've done something a little bit different with the formats. I actually created the formats to include what the code number was as well as the format. So I actually made a format that was 2:female, 3:died. And then we have all of our lab measurements that were taken both at time 1 and time 2. We have whether or not the patient died, whether or not the patient experienced shock, and we also took a difference between systolic blood pressure between time 2 and time 1. If we look down here, we see we have our descriptive statistics for all of the continuous measurements, and notice that for most of the measurements we do have complete data. So the first statistical procedure we're going to look at is PROC-CORE, where we can have SAS produce correlation coefficients. And so we're interested in producing a correlation matrix of systolic blood pressure at time 2, the cardiac index at time 1, heart rate at time 1, hemoglobin at time 1, and mean arterial pressure at time 1. And we're not changing any of the defaults. So let's take a look at what this output looks like. Here we see the full output from PROC-CORE. So first of all, we start out by just seeing some simple statistics on the variables that were included in the procedure. So we have the number, the mean, standard deviation, sum, minimum, maximum, and the label. And then we see that by default, SAS gives us the Pearson correlation coefficients. And notice that we have here, our first row is the actual Pearson correlation coefficient. So if we go over to look at the mean arterial pressure at time 1, we are looking at the correlation between the mean arterial pressure at time 1 and systolic blood pressure at time 2. And the correlation coefficient is about 0.42. The p-value, less than 0.0001, indicates that this is a statistically significant correlation coefficient, where we're testing the null hypothesis that the correlation coefficient differs from 0. And then finally, the n that was used was 113. By default, when we're doing PROC-Core, we do pairwise deletion, which means that the number of subjects that are included in an analysis depends on whether that subject has data for both of the variables that are being correlated. So here, when we're correlating cardiac index at time 1 and systolic blood pressure at time 2, only 110 observations had complete data for those two variables. However, when we look at the heart rate at time 1 and systolic blood pressure at time 2, we see that all 113 patients had complete data for those two variables. One of the assumptions to do PROC-Core with a Pearson correlation coefficient is that both variables are normally distributed. So if we're interested in correlating systolic blood pressure at time 2 with cardiac index at time 1, we are assuming that each of those variables are normally distributed. Now, let's say we're concerned that we do not have normality of one or both of the variables. Then the non-parametric method for producing a correlation coefficient is using Spearman's correlation coefficient. And so here, to request Spearman, we just write in Spearman in our PROC-Core statement. And the other thing I'm doing is I'm putting in this option no miss. And what no miss does is it does what we call list-wise deletion, which means that it excludes all observations that are missing values on any of these variables, so that in our output we will only see those observations that have complete data on all of these variables. Let's take a look at the output where we request the Spearman correlation coefficient and we want complete data on all of the variables, so only include observations that have complete data. So here we see that we're only looking at 110 observations. And notice here that instead of printing the sample size, the mean, standard deviation, sum, minimum, and maximum, like we saw when we ran PROC-Core before, because we're doing the Spearman correlation, we're getting the median, minimum, and maximum. So we're getting slightly different simple statistics. Also, notice here that we have, it's listed the Spearman correlation coefficient. And notice that we don't have a separate row for the n, because we know that our n is 110 for all of these correlations. So here, using the Spearman correlation coefficient, the correlation between systolic blood pressure at time 2 and mean arterial pressure at time 1 is again about 0.4 and is highly significant. The other thing I want to point out about this code that differs from when I did PROC-Core with the Pearson correlation coefficient is that when I have just a var statement, it does a full correlation matrix. It correlates every one of these variables with each other. If we have a var statement and then a separate with statement, in this situation, we're only going to have correlations between cardiac index at time 1 and systolic blood pressure at time 2, heart rate at time 1 and systolic blood pressure at time 2. So we're not seeing a full correlation matrix. And you can see this again in the output. We're only interested in correlating these time 1 variables with this one time 2 variable, systolic blood pressure. Let's say we were interested in doing a regression where we wanted to look at whether the mean arterial pressure at time 1 is predictive of systolic blood pressure at time 2. So to do a regression analysis, and here we're also asking for some diagnostics that I will go over, we're going to say proc-reg, and then we have a model statement, and our response variable goes first, followed by an equal sign, and then our independent variable or predictor variable, mean arterial pressure at time 1. And then I'm interested in doing a plot of the residuals by both the predicted values and the mean arterial pressure at time 1, or our predictor variable. And I'm requesting symbols with asterisks. And then I'm also creating an output data set called regdat, and what I'm outputting are my predicted values and my residual values. So let's take a look at what happens when we run this code here. So here is the output that comes from procreg. And we see that the p-value in the ANOVA table tells us if there is a significant linear regression. And in this example, we do have a significant linear regression because p is less than 0.001. The R-square tells us how much of the variance of the dependent variable can be explained by the independent variable. In this case, we have an R-square of 0.17, and this means that about 17% of the variance in time 2 systolic blood pressure can be explained by differences in mean arterial pressure at time 1. There's also an adjusted R-square, and that's not that important when we're doing a simple linear regression. An adjusted R-square is more helpful when we're looking at a number of predictors in the model, when we're doing multiple regression. And basically, the adjusted R-square imposes a penalty for having redundant or unnecessary independent variables. And actually, the adjusted R-square value will reach a maximum and then decline as additional non-statistically significant variables are entered into the model. But again, we're not focusing on multiple linear regression in this class, but I wanted to point out what the adjusted R-square was and where it is in the output. And then here are our parameter estimates. And the parameter estimates give us the information we need to determine the equation of the regression line. So our regression equation could be read as the predicted systolic blood pressure at time 2 equals 59.31, which is our intercept, plus 0.70, which is our slope, times the mean arterial pressure at time 1. Or we could say that for every 1 millimeter of mercury increase in the mean arterial pressure at time 1, the expected increase in systolic blood pressure is 0.70 millimeters of mercury. If we were to interpret the intercept, it is the expected value of systolic blood pressure at time 2 when the mean arterial pressure at time 1 is 0. And this is usually not of biological interest. Since this is a video, I thought it might also be easier if I put in the comment the interpretation of the regression output. So I've provided the equation of the regression line as well as my interpretation of the R-square. Now there are 4 assumptions to do a regression model. The first assumption is that the values of the dependent variable y have a normal distribution for each value of the independent variable x. Secondly, the variability of y is the same for each value of x. Thirdly, the relationship between the two variables is linear. And finally, the data are independent, and we know that by the study design. So the graphs that were produced by procreg are going to check for the linearity and constant variance assumptions. So here we have the regression analysis diagnostic plots looking at the predicted value against the residual and then the mean arterial pressure at time 1 versus the residual. So either of these plots can be used to check the linearity and constant variance assumptions. So in terms of equal variance, we're interested in whether the width of the point scatter is constant across values of our covariate. So if we look here, it appears that the width of these points are constant. We don't see any kind of pattern here, so we could conclude that the equal variance assumption has been met. And then in terms of looking at linearity, we're interested in whether there appears to be a random scatter of points about the y equals 0 line. So there's no obvious pattern. So again, it appears that our linearity assumption is met. So again, for equivariance, we're interested in the width of the points. And for linearity, we're interested in whether there's a random pattern around the y = 0 line. So based on these